Hello everyone. In this part 4 of the problems, we're going to conclude with some problems that are related to both rate of change and also volumes and surface area. So initially we consider question 13. We have a 5.5 foot tall man is standing X feet away from an 8-foot street lamp. So we have this diagram here that represents the situation. We have the street lamp here. The man is standing X feet away, and the shadows projected S feet away. Now, we want to use similarity of triangles to determine the length of the man's shadow, which is depicted here, and write an equation that describes the length of S in terms of X. So we can do that by setting the similarity of triangles. So we have two triangles here. We have the big triangle that goes here, and where the man's standing, a second triangle is generated, the small one. This measures S, this measures X here, and we know that the man is standing here, and the street lamp is here measuring 8. So we don't know the quantity that the man is going to measure, right? And if we assume that this is 5.5 foot man, then we can say that this quantity here is going to be 5.5. So now the shadow over this 5.5 is going to be equals to X plus S here over 8. And so with this relationship, we can now find out that 8S is 5.5 X plus S. Okay, and this is one relationship that is going to describe S in terms of X. Okay, now if the man is standing 3 feet away, so now that transform X into 3. So we will have AS is 5.5, and this is 3 plus X. Right? So from here we can actually find out what S is. And we can say 8S is 5.5 times 3 plus 5.5 times S. And so this is here 16.5, 5.5S, 8S. And so solving here, we get that 2.5S is equals 16.5. And that's going to imply that S is going to be 6.6. Okay. So the measure of the shadow here will be 6.6 feet. Now, if the man is walking away from the lamppost, and let me just put this one here. And if the man is going away 1.5 feet per second, so this is going to give us how much X is increasing. So X is increasing by 1.5 by time in seconds. And remember that we initially have 3 feet away. So we have 3. So we have an equation that describes X in terms of t, and it's a linear piece. We have initially 3 step away, and then we have 1.5 feet per second. So that gives me the distance of the man from the lamppost after t seconds. Now we want to know how long will the man's shadow be after 2 seconds. So we pretty much just plug here t in 2. And so that will be 6. So that will be the length of the shadow here. It will give me the x. And so once that we have the value for x, then we can find out, again, using the equation above, using this equation again, how long s is going to be. So we use s over x 5.5 equals x plus 6 over 8. And so if we solve here for x, you're going to find out that ax is 5.5 s plus 33. And then solving a little bit more, 2.5 s is equals 33. And that implies that s is going to be 13.2 feet. Finally, we want to know how fast is the length of the shadow growing as the man is walking. And so to check that, we can check a couple points. So we start with t1 equals 0, and we go with t2 equals 2, since we can check after 2 seconds. So s1, or the shadow at t equals 0, was 6.6, right? And s2 was 13.2. Remember, we're using this value that we got in 0 seconds, pretty much, or the initial time. And then we're using this 13.2, that is after 2 seconds. So now we do the change in s over the change in t. The change in s is the difference between the two s, and the change in t will be, of course, the change between the two times. So here we have 13.2 minus 6.6 divided 2 minus 0. And if we compute this in the calculator, this will give us 3.3 feet per second. Remember, this is a measure, the top is a measure of feet, the bottom is a measure of seconds, so that's why we obtained that rate of change is in terms of units of feet by units of seconds, or units of length over units of time. Now that for question 14, we have that you wish to design a dish in the shape of a cylinder with no top. However, we do have a bottom. So the dish must have a volume of 80 cubic inches. So the total of the volume is 80. But remember, this is a cylinder, so the cylinder is going to be pi r squared times h, right? That's the volume of the cylinder. And at the same time, we want to find the radius of the vase and the particular height of the dish that minimize the materials that are used, or that is minimizing the surface area of the side and the bottom. So remember, every time that we're doing a cylinder, this is coming from a sheet, and the sheet has a length of 2 pi r, and this is the height. And so now this is the height here when we turn it around, and this is radius r. Now, because we don't have a top, we don't have to worry about having a lid, but we do have the bottom of the dish. So we need to compute the surface area of also a circle of radius r. So of course, the area of the circle is pi r squared, and the area of the sheet that we use for the cylinder will be just the multiplication of the base by the height. So it will be 2 pi r times h. So the total area, or the surface area of the cylinder, will be given by pi r squared from the circle, and 2 pi r h, and that is coming from the sheet. Okay. Now this has an issue because this is still a function that depends on r and h. So we need to transform it in a function that it has a single variable. So because we have an amount for the volume, we can say, well, h is 80 over pi r squared. And so this relationship between the height and the radius is going to allow us to have a surface area function that it just depends on r. And this is just going to be now pi r squared plus 2 pi r, and now we replace h by 80 over pi r squared. Notice that at this point, then we have a function that we can check for what's the maximum. This is a quadratic function, pi r squared by 160 pi, or actually I'm going to lose the pi here with this pi below, and I'm going to lose 1r with 1r here. So this is just going to be 160 over r. Now, you can check in Desmos for, again, what this function is going to provide, and you're going to find that this is a function like this, and it's going to have a minimum that it comes at the point 2.94, 8150. And so from that, we can find what the minimum surface is, which is this one. So this is the minimum surface, and this is the minimum radius that we're going to find out. And from plugging this in h, we're going to find out that the minimum h is going to be 2.95 inches. So that's how you go about finding the minimizer for this. Remember, you can use any graphing device for finding the chart of this function. So whether you use a calculator or Desmos, any of these two works. Now, question 15 is about using rate of change with a little bit of the volume. So we're gonna go with initial conical tank that is going to be 6 feet deep and 4 feet across the top. So that means that the radius here, the top, is really 2 because the complete thing is 4. And what we do is we're calculating what happened with the volume of water that is in there. So as you can see from this diagram, we're going to have a similarity of triangles as an area. We have a piece of the cone, and we can check here where the water is coming. And we're not going to know what this radius is, and we're not going to know what this h is, what the height is, what the deep is. But we know that the tank has a measure of 6 feet, so we have enough information about the large triangle versus the little triangle here. So you can say r over h is equals to 2 over 6. And with this, we have a relationship that establishes how much r is in terms of h. Now, we can also work with the volume. The volume is going to be 1/3 of pi r squared h. And if we replace again the values of r in terms of h, then we're going to have 1/3 of pi, 1/3 of h squared times h. And multiplying this here, 1/3 squared is going to be 1 over 9. So this is going to be 1 over 27 with this pi here, pi over 27. And this is h squared times h is going to be h cubed. So we have now a formula for the volume of the water tank in terms of only h. Now for B, we want to determine a formula for the average rate of change for the volume in terms of the change of the height. So what's going to happen is that first we're going to establish what is the change in the volume. So for that, we're taking two different volumes at two different instances. So that means that we're going to have two different heights. So we have pi over 27 h2 cubed minus pi over 27 h1 cubed. As you probably can guess, we factored the pi over 27, and now we're going to have a difference of cubes here. And so if we establish the difference of cubes, we factor the difference, and we're going to get h2 squared plus h1 times h2, h1 squared. And by the difference, delta h, which remember is just a2 minus a1. Now at this point, then we can find out what the rate of change is, the average rate of change. The delta of b over the delta of t is just going to be pi over 27 h2 squared plus h1 h2 h1 squared delta h over delta t. Now at this point, for C, we got information that the tank was initially empty when the water began flowing into the tank at 3 feet cubic per minute. Notice that this is cubic, so that means that this is a measure of how much delta B over delta T is, because it's cube. So it's a measure of volume. And since it's per minute, we know that it's a measure per a measure of time. So now, what is the average rate at which the water level is rising between h equals 4 and h equals 5? This is giving me the information here for this h2 and h1. So we can set up dv dt being 3. So 3 is equals pi over 27. And so h2 is going to be 5. So this is 5 squared times 5 by 4 plus 4 squared, since we established the two heights. And now we don't know what delta h divided delta t is, but we can find out here. So now dh dt is just 3 times 27 over pi, and this here is going to be 25 plus 16 plus 20, so this is going to be 61. So at the end, dh dt, we plug this in the calculator, we're going to find out that this is 0.423 feet per second. So between 4 feet and 5 feet, the water level is rising at 0.423 feet per second. Now last, we have a similar scenario, but instead of checking for rate of change, we want to check what happens if we inscribe a cylinder inside of a cone. So we want to find the dimensions of the cylinder of maximum volume that can be inscribed in a cone of 10 inches and a base of 16 inches. So just from this, we take a transversal section and we take it in half of it. We have the triangle, and we're gonna feed here a square that is representing the piece of the cylinder that we're getting. So let me actually so here we have what represents the transversal section of the cone. And now here we feed the piece of the cylinder. So of course, we set up some dimensions for this. We're going to set this called R. We're going to call this H. And we do have information about the external pieces. This is 10. And because this was, the whole thing was 16, the diameter, so this is 8. Now, however, we don't know how much this piece here is. We can compare the big triangle with the small triangle by similarities. So we want to compare the big triangle with this one here. Now, this base from here to here, of course, measures 8 minus r. Why? Because the whole thing is 8, right? The whole thing is 8. And we're subtracting this piece here that measures r. So now we know that a minus r is to h as 8 is to 10. Just by similarities of this small triangle to the big triangle. So that will be 10 times a minus r equals to 8h, or we can see h as 10 over 8 minus r. Now this gives me the information of h in terms of r, which is good for putting a function in terms of a single variable. Now we're trying to maximize the volume of the cylinder. So the volume of the cylinder is pi r squared times h. So now we can see this as pi r squared times 10 over 8 a minus r. So of course this is exactly the same type of thing that we've been doing with everything. We can simplify this a little bit, and this is going to be 5 pi over 4 r squared a minus r. And again, you can put this in Desmos or any of your graphic devices, and you're going to find out that this is a cubic formula, and that cubic formula is going to have a certain point, is going to have a maximum, and that maximum is going to be located at the point 5.33, 297.87. And this is a measure of the radius, of course, and this is a measure of the volume. So this is telling me what R to use to get the maximum volumes. So when the cylinder has dimensions radius 5.33 in h, you can actually plug this R here in h, and you're gonna get that h is approximately 3.34. Then you're gonna have a maximum volume of 297.87. All right, and so that concludes all the problems for the exam 4 review. Make sure to try and do these problems on your own before getting to the answers and comparing to the things that we have in these videos and the solutions. And once that you check the difference, or you can check what you're doing okay, then you can go ahead and find a little bit more of feedback of how to complete some of these questions. See you at the exam.